Does anyone ever use this board? That's hysterical. I have to expect it to raise it up and see an elf back there, you know, like a, hello. Oh. What is it for, actually? What could you possibly use this for? Huh? Oh, announcements. Oh, I should have put all that stuff here. Next time. Oh, also there's one on the other side. Excellent. Oh, my mic is working. I believe my mic is working. Alrighty, shall we start? All right, excellent. So starting today, there will be content in the lectures. I promise. And actually, if all goes well, by the end of today's lecture, we'll really cover a decent chunk of what normally takes half a year or a year of a quantum field theory course. From a very different point of view. You'll see what I mean. And hopefully by the end of this lecture, you'll understand why, on completely general grounds, whatever the ultimate theory of the world is at very high energies, if at low enough energies is described by a finite number of particles interacting in some way, it must be a theory of interacting particles of massless particles of spin 0, 1/2, 1, 3/2, and 2. And we'll discover that the consistent interacting spin 2 theories have got to be described by general relativity. Massless spin 1 has got to be Yang-Mills. Massless spin 3/2 is supersymmetry. All of these things we discover as the answer to an algebraic problem. Okay, once we set things up by directly putting in compatibility with the basic principles of Poincare invariance and unitarity. But so this lecture and a few of the lectures going into the end of next week are going to be developing the responsible direction of this subject. Okay, so again, there are two things going on. There's the responsible direction where you use symmetries to constrain the answer and then everything you know to determine the structure from singularities and other arguments. And that's very important because we'll use it to actually learn what consistent theories are and actually do calculations and get data. Then there will be the irresponsible part of the subject, which is to cast around for interesting mathematical structures that spit those things out, okay, so that we can see them coming out rather than going in as primitive things. So we're going to go back and forth between responsibility and irresponsibility a lot. But today is all responsible. So the references for today's lecture, the first part will review the story of what is a particle and the Vikner little group and so on. This is really beautifully done in Weinberg Volume 1 in some early chapter, I don't remember. The second part, where I'm going to talk about 3 particle amplitudes and the consistency conditions on 4 particle amplitudes, this is part of the sort of lore in scattering amplitudes land, and I've listed some papers in inverse historical order. This is a paper that's mostly about a general formalism for both massless and massive scattering amplitudes, but which reviews the story somewhat quickly, but I think in a quite pedagogical way. This paper does in a lot more detail, and many of the pioneering ideas go back to that very early paper of Cacciazzo and Benincasa. All right, so first, what is a particle? And to a professional theoretical physicist, a particle is an irreducible representation of the Poincare group. Okay, so and that sounds a little fancy, but it's actually very close to what we intuitively think as a particle. You know, you intuitively think maybe a particle or something, some excitation of the energy that's sitting there. Maybe it's moving with some momentum. Maybe it has some spin. But the reason we even use those labels to describe what a particle is has to do with the symmetries that space-time has, which for some reason is Poincare symmetry. After all, the reason we give a particle sitting here, the electron, the same name as a particle sitting there, the electron, the reason we use the same word, the electron, is because of translational invariance. The reason we say an electron moving this way versus that way is still an electron is because of rotational invariance. Okay? And had you turned on a gigantic magnetic field in this direction, then it would actually be kind of dumb to call both of them electrons, because they actually do totally different things if they're going this way than if they're going that way. Right? So our very notion of what a particle is goes to symmetries of space and time and their unitary representation on a Hilbert space. So in the next 15 minutes, we're going to talk about unitary representations of the Poincare group. And to begin with, we're just going to diagonalize translations. That's what we normally do when we label, and most naively, when I say that a particle is some one particle state with momentum p mu, we do this so that a translation by amount a mu acts on this as simply as possible as a phase. Okay, so I probably won't write the mu index over and over again, but so that's why we label things. Now, Vikner's question is, what other labels could a particle have? Okay, so the other labels are called sigma. I think I'm following Weinberg's notation here. And before doing anything formal, let's just think about it intuitively, right? We know that somehow the particles have spin. Okay, and so we should talk about that. We also know there's a qualitative difference between the spin degrees of freedom when particles are massive and massless. Okay? When a particle is massive, like a spin 1 particle, like the W or the Z, no matter how it's spinning, no matter how fast it's moving, there's a frame you can go to where it's at rest. And on that frame, by doing a rotation, you can see it spin in all 3 directions. So a massive spin 1 particle has 3 degrees of freedom. But famously, a massless spin 1 particle, like the photon, you only get to talk about polarization or helicity. That's because you can never catch up with it. And so all you can talk about is its spin in its direction of motion or opposite to its direction of motion. That already tells us there's going to be something interestingly different between massless and massive. And so a massless photon has 2 degrees of freedom. In fact, most primitively, it has 1 degree of freedom, because we can't even flip what I mean by the helicity in this direction and the opposite one. The only reason we assume they're both there is because the theory has parity. Okay, and if we talked about chiral fermions instead, it's not even true there, right? We're allowed to have just left helicity fermions without having the right ones. Okay, so most primitively, massless particles just have 1 degree of freedom, just labeled by their helicity. And this difference between massive and massless, as we'll review in a second, is really at the heart of much of the drama of 20th century physics. Okay, this fact that to describe massless particles is difficult. There's this discontinuous drop in the number of degrees of freedom. First of all, puts an enormous amount of extra structure that's needed on the description of theories of massless particles. That in the usual Lagrangian formalism that we will not be talking about, in the usual Lagrangian formalism is associated with the introduction of large amounts of redundancy, gauge redundancy, diffeomorphism redundancies. Okay? That is precisely because there's this degree of freedom drop. And secondly, the fact that some particles are massive is famously associated with things like the Higgs mechanism that then tries to make sense of this discontinuous difference between massive and massless. In this course, we'll almost exclusively be talking about massless particles. There's a lot to say about massive ones that would make very nice topics for some of your papers if you're interested. But anyway, we'll focus mostly on massless particles. But let's just say intuitively what the answer is supposed to be. The answer to this question is that somehow this label sigma should represent something like just spin when the particle is massive and something like helicity when the particle is massless. And we'd like to see how that comes out sort of more formally from this question of the representation of the Lorentz group. So let's say we have a Lorentz transformation that might take a momentum p mu to some lambda mu nu p nu. This is my Lorentz transformation, so we won't really use this, but there's some metric, and it leaves the metric invariant. Okay, so most naively, what I'd like to do, so these lambdas form a group, and I'd like to associate with every lambda some unitary operator u of lambda. And so I would like to know how that unitary operator acts on the Hilbert space. So what's the most naive thing that you would imagine? What is u of lambda on p sigma? The absolutely most naive thing that you might imagine would be what? Well, you might think, is this lambda p and sigma? Okay, that's the dumbest thing it could do. Obviously, it changes p to lambda p. But that cannot be that would be the answer for a spin 0 particle. And sigma could be some other degree of freedom, charge, color, some other degree of freedom. But that can't be the right answer, because, for example, we know if I have, let's say, a photon going in the z direction, if the Lorentz transformation happens to be a rotation around the z direction, then it needs to pick up the phase associated with the fact that it has spin 1. So this cannot be the answer. We have to imagine something a little more general than that. And so to actually imagine the most general thing you could have, what Vikner did is the following. He said, no matter what your momentum is, choose some reference momentum k mu, some reference momentum, and choose some way of representing a general momentum as a Lorentz transformation that will depend on p and k in general on this reference guy. So I'm making a choice. This is not unique. There's lots and lots of ways that I can represent the given momentum as a boost of a reference one. For example, after I'm done, let's say I have a photon moving in the z direction, I can rotate around the z direction. That's not going to change. So the L is not unique, but choose one. All right? Having chosen one, this is now a definition. I'm going to say that I have my states k sigma, whatever they are, and then Vikner defines. He says p sigma is defined to be whatever this unitary operator is u associated with that Lorentz transformation, L of p and k on k and sigma. This is a definition. OK? So the important thing here is that this is a definition because it's telling you how to compare the sigma labels. Okay? It's the same sigma label. It does not change from one side to the other here. If you like, this is just defining what I mean by the sigmas at boosted p starting from some reference guy. Is this clear so far? So now we're done. We've defined the states, and now I can talk about what a unitary transformation does. OK? And so now let's look at a general u of lambda on p and sigma. Well, this is u of lambda, u of L on k and sigma. And now it's clear what I want to do, right? I want to write this as u of L of lambda p on k and sigma, because I know that it's going to take the momentum to lambda p. But I can't do that, right? I mean, it's not that. So let me write it as u of L of lambda p and k, and then just multiply by the inverse of that here. So u of L of lambda p and k inverse lambda L of p and k on k and sigma. Right? So far, this is just a trivial identity. I just put in the identity on this side. But now look at this sucker here. Who is this? This is some composition of Lorentz transformation. What does it do? It takes k to p to lambda p back to k. OK? Therefore, whatever the heck this thing is, let's call it w. It depends on all this crap. I won't keep writing it. But w is something that leaves k invariant. So there's some transformation w such that w mu nu k nu equals k mu. This is called the little group, or Vikner's little group. The little group associated with the momentum k. And therefore, u of w, whatever it is, u of w on k and sigma cannot change k. It can change sigma, but it can't change k. So this is going to be some d sigma sigma prime that might depend on w. It won't change k. It might change sigma prime. All right? And so this d is therefore a representation of the little group. So now we've gotten the answer to our question, right? What are these labels? The extra labels that we can associate with particles are representations of the little group. Okay? So we have to figure out what the representations of the little group are, which now depend on whether the particle is massive or massless. Now, what happens when the particle is massive? The particle is massive, so let's say I'm in d spacetime dimensions, capital D spacetime dimensions. Then if it's a massive particle, I can choose my reference momentum to be k mu to be m0. OK, so who is the little group? It's just spatial rotations. OK? And so the little group in this case is just SO d minus 1. Right? And therefore, for massive particles, the labels are spin. They're labels of SO d minus 1. In 3 dimensions, just of ordinary rotations, they're just spin. But what happens for massless particles? For massless particles, the little group is different. So let me just write it out in 4 dimensions. And let me just see sort of what it is infinitesimally. So I want to say that my lambda mu nu in general is some delta mu nu plus some omega mu nu. This is infinitesimal. OK? And I have to have that omega mu nu with downstairs indices is antisymmetric. So that's what it means for it to be a Lorentz transformation. Okay? So now I'm looking for some omega mu nu that now annihilates k mu. So I'm looking for infinitesimal Lorentz transformations that annihilate k mu. And now let's ask what those are. So let's say that my k, my null k, now I have a null k. So say that my k mu looks like 1, 1, some overall e, it doesn't matter, and then 0, 0, let's say I'm in 4 dimensions. Then what does omega, I can lower the mu index, it doesn't matter. So I'm looking for an antisymmetric matrix omega mu nu, k nu equals 0. But k looks like that. So what do these matrices look like? Well, it's an antisymmetric matrix. But in the upper 2 rows, it looks interesting. In order for that to happen, it has to look something like A, negative A, B, negative B, and then C, negative C. And then here it's antisymmetric. Okay, so that's the most general matrix that annihilates that the vector 1, 1, 0, 0. Okay? It has 3 degrees of freedom, okay, as it should. In other words, the size of the little group is not different, right? It was rotations. It has 3 generators. Also, when it's massless, it has 3 generators. So it's generated by these matrices that I can call Tx to be the one with A. So let me just write it, the one with A. Ty, that's the one that's associated with B. And obviously, Jz is just the rotation in the direction that the particle is moving in. OK, so Jz is the one that's associated with C. But now you can very easily verify what is the algebra. Okay, and the algebra is, you can just see trivially from this matrix that Tx and Ty actually commute with each other. But Tx commutes with Jz to give you a Ty. Maybe there's a sign. And Ty commutes with Jz to give you a negative Tx. In other words, Tx and Ty are just a vector in 2 dimensions. So their commutator with Jz is just like a vector in 2 dimensions. But they commute with each other. OK, does anybody recognize this group? This is just the group of symmetries of the Euclidean plane. Tx and Ty are translations in x and y. And Jz is a rotation in the Euclidean plane. All right? So that's it. It has exactly the same size. I forget what it's called, IS or whatever it's called. I don't care what it's called. But just the group of symmetries of the Euclidean plane is a little group for massless particles, whereas 3-dimensional rotations is the little group for massive particles. And a very nice exercise that you should do is to sort of intuitively see where that comes from by actually computing the little group, the generators, not for a massive particle at rest, but for a boosted massive particle. And what you'll find if you compute the little group for a massive particle is that you're getting the symmetries of a sphere, but you are blowing up the radius of the sphere more and more and more as the boost gets larger and larger. OK, so of course, at any finite radius, you still see 3-dimensional rotations. But in the limit, as the radius of the sphere goes to infinity, which is infinite boost, the rotations in the x and y axes just turn into translations of the plane. And you get a contraction of the rotation group in this way. So, all right, so that's the little group. See, it has the same number of generators, but it's different. It's qualitatively different. It's a contraction of the little group for massive particles. OK, so now let's talk about representations of this little group. And it's even simpler than representations of rotations. You don't have to remember anything from quantum mechanics class for rotations. Tx and ty commute with each other, so we can label any state by the eigenvalues they have for tx and ty. Okay, so here this is a two-dimensional plane. This is now the eigenvalue of tx and the eigenvalue of ty, and so I can label a state. There's a state that has some eigenvalues of tx and ty. But now the problem is that let me do a rotation, a z rotation on that state. If I do a z rotation on that state, if I have this state, I have a continuous infinity of other states as well. Okay, so a generic representation of the massless little group does not have a finite number of particle species. It has an infinite number of particle species. Okay, and the better way of doing it is to go to Fourier space on the circle, and you have an infinite tower of massless particles. So you can think about this irrep of the little group as somehow being an infinite tower of massless particles of higher and higher spin. These are called continuous spin representations, and they're still mysterious. We don't actually know if they really make sense. This is a subject that people worked on in the 70s. There are all kinds of BS reasons people threw them out. The reasons that people threw them out in the 70s are not really good reasons. Philip Schuster and Natalia Toro, actually, when they were grad students here, began to write some nice papers to try to make sense of these things. It's still not obvious if they actually make sense. But in any case, we've never seen anything like it in nature. That's not a very good argument. But they're strange. They're funny, so we're going to ignore them. Right? Yeah, well, that's right. So you labeled by the overall eigenvalue. Okay, so so if we don't want to have these infinite particles, then we have to do something. We have to choose the eigenvalues of tx and ty to be at the origin. Okay, so if we nail tx and ty at the origin, then what's left is just the eigenvalue under jz, and that's helicity, right? So that's how we see that that's how we see that there's this drop in the size of the little group. In 3 dimensions, for massive particles, it's SO3, but for massless particles, it's SO2, okay, just the U1. And in general, for massive particles, it's SOD minus 1 when it's massive, and SOD minus 2 when it's massless. Okay, any questions about this?
Sorry, why do you have 2 ellipses?
Well, we don't. We only have 1. So and in fact, if we have fermions, that's completely correct. We have chiral fermions. We only have 1. We don't have the other. The reason we have 2 for photons is more detailed. That it turns out, and as we'll derive from at the end of the lecture, there are no consistent theories of chiral massless spin 1 particles. Okay, so the only way you can have consistent theories of massless spin 1 particles involves a parity for them. So you have to have both. Okay, so most primitively, just from representation theory, you only have 1. But with the assumption of parity, you have 2. Is that any more questions about this? All right. So now, this drop is really important. So let me just spend a microsecond, slightly more than a microsecond, talking about how we deal with this drop in the standard way of doing field theory. You see, let's say you're someone, you're learning quantum field theory, or maybe you're just deciding that you want to play around with Fineman diagrams to build amplitudes. They look nice. What do? You do some calculations. You have photon, Compton scattering, some funny diagrams like this. But these are photons, massless spin 1 particles on the outside. And whatever you learn in your courses about Fineman rules, blah, 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 are some Lorentz tensors, right? Everything is made out of 4 vectors. So you're going to get some expression here that has Lorentz indices, mu1, mu2, blah, blah, right? And we even call that a Fineman amplitude. That is not an amplitude. So this is the number 1 thing to take away from the first 15 minutes of this, slightly longer of this class, is that amplitudes are not Lorentz tensors. They're not objects that carry Lorentz indices. They carry little group indices. So they have to have an interesting transformation property that when you do a Lorentz transformation on the momenta, they pick up a little group transformation on their little group indices. Okay? And that's not what we get from Fineman diagrams. What we get from Fineman diagrams are just good old-fashioned objects that transform nicely under Lorentz transformations. Okay? So that's why we invent something called a polarization vector. Okay? And that's a sort of fingerprint of quantum field theory, this idea that there are underlying fields, and then you put them on shell to make particles. Right? that is associated with this notion of a polarization vector. So the purpose in life of a polarization vector is to be something that is like a bifundamental. It interpolates between the Lorentz group and the little group. So you say, let's say I have a massless particle, it has some helicity h. Then I contract this with a polarization vector to now get something which does do what it's supposed to do, right? The purpose of that is that if you do a Lorentz transformation, epsilon will now pick up this phase. It'll pick up this phase to act with the little group. So in order for this entire Lagrangian Feynman diagram picture, local space-time evolution, all this stuff to make sense, we have to believe that there are these objects called polarization vectors that are kind of intermediaries between the Lorentz group and the little group. For massive particles, no problem. How do I describe a polarization vector? Let's say for a massive spin 1 particle. OK, here's epsilon mu for some momentum p. And already you're nervous, because epsilon mu has 4 degrees of freedom. But you know that the massive spin 1 particle only has 3, right? Just the spin. So what do? You say, it's actually a constrained 4 vector. It satisfies p mu epsilon u equals 0. OK? It's already slightly unpleasant that you have to deal with these constrained objects, but it's perfectly fine. It's perfectly well defined. There's exactly a 3-dimensional space of solutions of p dot epsilon equals 0. And if you do a Lorentz transformation on the p, those epsilons are acted on by a rotation. Exactly what they're supposed to do. Is that clear? All right, now, let's try to do the same thing for a massless particle. Now we're screwed. The massless state has 2 polarizations, and there's plainly nothing we can do. Right? I can't do anything. I can't put any more constraints on the epsilon to go down to 2 degrees of freedom. Right? So I claim there's no such thing as the polarization vector for a massless spin 1 particle. You say, what the hell are you talking about? I know what they are. I've known what they are since I was in kindergarten. And here it is. If the particle is moving in the z direction, because I'm so smart, I even put root 2s and i's and crap like that. And I say, this is the polarization vector, epsilon mu plus minus. Right? That's a polarization vector for a photon of helicity plus or minus moving in the z direction. What's the problem with this? Anyone have some nasty comment to make about this formula? You should. That's right. This does not transform like a 4 vector. These zeros are total crap. They don't mean anything. If you do an appropriate Lorentz transformation, in fact, exactly a little group transformation, and I invite you to do this, to do a transformation that involves a boost, a translation, a boost back, sorry, a boost, a rotation, a boost back, and a rotation back, to bring the momentum back to where it starts. If you do that sequence of transformations, you don't send this back to something of this form again. Those zeros are filled with something now. Okay? And how could it? There's no way of picking out this, because there's no Lorentz invariant way of specifying that. So, but what does happen? What does happen after you do that sequence of Lorentz transformations to this guy is epsilon will not come back to itself. But what does it come back to? It comes back to itself plus something proportional to p mu. Okay? So that's why we have to introduce this new idea. If we want to describe massless particles in this way, we have to introduce this interesting new idea that to describe a massless particle of spin 1, it's not described by just this 4 vector epsilon. That's not Lorentz invariant. But this entire equivalence class of epsilon mu, where you identify epsilon mu with epsilon mu plus anything times p mu, that whole equivalence class is now Lorentz invariant. Okay, now if you do a Lorentz transformation on that guy, it'll come back to itself in that equivalence class. Okay? Now, some decent fraction of you will recognize this. Right? This is a gauge transformation in standard language. Right? If I go back to momentum, to position space, this is a mu is identified with a mu plus d mu something. Okay? And so we see from this point of view how explicitly that it's a redundancy. It's a problem with us, with human beings. We are trying to describe things using these polarization vectors, and we're bonked on the head by the symmetry and say you can't. If you're going to describe it this way, you have to make it redundant and say it's this whole class that you have to use. Okay? And so that means that if you're going to play games with Fineman rules and so on to build amplitudes, you thought you had fooled yourself to thinking that all you had to do was make these nice tensors and then contract them with polarization vectors, and you'll get a Lorentz invariant answer. And you won't, because you have to make sure that the answer does not depend on which epsilon in this equivalence class you chose. right? And that in turn means that the objects you build have to satisfy an amazing identity. That if you take any one of these indices, if it's massless spin 1, and I replace this change, that means that if I take this index and I contract it to its p mu, I should get 0. Right? So you have to have identities that look like p mu, m mu, and then any number of other indices here is equal to 0. Now, from the conventional point of view, these things are called on-shell word identities. And when you come from a gauge theory and you know about Lagrangians and you like gauge symmetry for some reason because it's beautiful and lovely, blah, 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 this is an output. Okay? And you notice at the very end, with relief, that this allows you to talk about the dynamics of these massless particles in a genuinely Lorentz invariant way. Okay? And building theories that make this happen is not easy. If you're just screwing around with Fineman rules, who cares about gauge symmetry, pretty things? Just write down random Lagrangians, random Fineman rules. Then you'll get things that are naively Lorentz invariant, but will fail this constraint. It will not be physically Lorentz invariant. And then you'll find very special theories that satisfy this. And those very special theories are Yang-Mills theory and general relativity and so on and so forth. Okay, so that's a path from the conventional way of thinking about things that shows you the power of this constraint on the underlying nature of the Lagrangian. Okay? That's actually a very nice project. If someone wants to do a paper on this sort of intermediate way of taking this Feynman diagram philosophy and imposing these things to see how we get the theories that we know and love, that's roughly what Weinberg did with soft theorems in the 1960s and has been done in various ways by other people since. And doing it all the way to the bitter end has still not been done. I sort of did it in my quantum field theory course here 15 years ago. Okay, but I think it's not really in the literature in total generality. It's a very nice thing to sort of develop. But we're not going to do things that way because it's not really morally correct. Okay? The real problem here is that we've made a mistake from the very beginning of forcing ourselves to describe things in this way. You see, this means that you've never seen an amplitude before if you've taken a quantum field theory course. If you've seen a polarization vector, you haven't actually seen an amplitude. You've only ever seen a redundant representation of one. All right? So now our goal for the next half hour is to actually see amplitudes. Okay? Any questions so far? All right. So in other words, what we now want to do is find a way of talking about amplitudes where just their pure kinematical properties, their behavior under the little group, the fact that when you do a Lorentz transformation on the little group, a Lorentz transformation on the momenta, you pick up a little group transformation on the amplitude is manifest. And that is the purpose in life of the so-called spinor helicity variable. So this is our next topic. Often this subject is introduced as kind of a trick. You notice a cool way of representing on-shell momenta, et cetera, but it's not a trick. Its conceptual point is that these are the variables that manifest the correct kinematical property of amplitudes of transforming under both the Lorentz and the little group. So before doing that, we're first going to talk just about ordinary Lorentz transformations. So given any 4 vector, massive or massless, it doesn't matter, any 4 vector p mu, they're a way of associating a 2x2 matrix with it. You've probably seen this even for ordinary rotations. Now, where we take a 3 vector and dot it with the Pauli matrices. Well, if you add the identity to the set of Pauli matrices, you can make a 4 vector out of it. If you've never seen it before, it doesn't matter. We're just going to write down what these things are. And so what you get is a 2x2 matrix p0 plus p3, p1 minus ip2, p1 plus ip2, p0 minus p3. OK? So let me, for the moment, call this matrix, I don't know, let me give it another name. Bold P. OK? That's a 2x2 matrix. Now notice, what properties does this matrix have? It's a Hermitian matrix. It's furthermore the most general 2x2 Hermitian matrix I can possibly have. Right? Because this is the complex conjugate of that, and whatever these are, I can write them as something plus something and something minus something. Right? So this P matrix is the most general 2x2 Hermitian matrix you could have. Therefore, there is an obvious natural thing. What if you just conjugate it? Okay, if I just conjugate this matrix with a random complex matrix, not unitary, just a random complex matrix. So if I send P to some L dagger P L, then this new matrix is also Hermitian, no matter what L is, right? And therefore, this new matrix also looks like sigma dot some other p, right? So this is going to be some sigma mu, some p mu prime. Is that clear? OK. Now comes the key point. What's the determinant of p under this transformation? So the determinant of p prime, so this is p prime. The determinant of p prime is just the determinant of L mod squared times the determinant of p. OK? So let's say I choose the determinant of L to be 1. Okay, so this is now not a completely random 2 by 2 complex matrix, but a special 2 by 2 complex matrix of determinant 1. Okay, so if L is in SL2C, then the determinant of P is equal to the determinant of P prime. But what is the determinant of P? Well, very beautifully, of course, the determinant of P is just P squared. OK? So what we find is that this is a transformation. So this transformation on the 2 by 2 matrix induces a transformation on the momenta that leaves p squared invariant. So it's a Lorentz transformation. Okay? And that's how we see that Lorentz transformations in 3+1 dimensions are the same as SL2C. So this, in fact, gives us the and the two component vectors that this L acts on are the spinor representation of the Lorentz group. OK? Now, we can actually be more general about this if we imagine just totally complex momenta. If we do just complex momenta, then we can more generally look at P goes to just a different matrix on the left and the right. Any matrices on the left and the right, and so long as they have determinant 1, still p squared will be invariant. So that tells us that the complexified Lorentz group, so we saw the ordinary Lorentz group, the Lorentz group of 3-1 signature is SL2C. The complex Lorentz group is 2 copies of SL2C, one for the left and one for the right. OK? And finally, there's one last thing that we can do, which is fun. Let's just get rid of the I there. If we get rid of the I, then we just have a completely general 2 by 2 real matrix. OK? And so if I do everything over the reals now, no i's, then what is the determinant of P? It's P0 squared minus P3 squared minus P1 squared plus P2 squared. So 2 minuses and 2 pluses. That's 2, 2 signature. OK? So when everything is real, we also learn that the Lorentz group of 2, 2 is 2 copies of SL2R. And these will all be important for us. OK? And we're going to actually do a lot of things implicitly with real variables in 2, 2 signature. But the point is there are 2 SL2s here in general. And it's just that they're getting identified. Okay, so in the complex, there's 2 SL2s, and the real Lorentz group is the diagonal subgroup of them. And in 2-2 signature, they're just 2 independent SL2s. Okay, so far this is just kinematics. And let's talk about what the Lorentz invariants are. Well, SL2 is especially nice because the only invariants you can build are contracting with the epsilon symbol, right? So here are the invariants we're going to see. And we're going to have our first introduction to the bracket notation here. In this entire course, all the spaces that we're going to be working with will not have any metrics. They're all spaces where the only invariants are the epsilon symbol. So the only way to contract things is with the epsilon symbol, determinants. And so everything that's contracted will be put in a bracket of one sort or another, and you will know what we're talking about by what the bracket looks like. We'll not see any dot products almost ever, okay? But we'll see brackets up the wazoo. Okay, so for example, here let's say, actually, I'll come to the. Let me delay a second talking about the invariants. So let's now come back to talking about massless particles. So let's say I have a particle p where p squared equals 0. That means that the determinant of this p matrix is equal to 0. And that means that this p matrix has rank 1. Okay, so I can write it as the outer product of two two-dimensional vectors. So now I'm going to use a notation. Instead of writing it in bold p, I'll write it as p alpha alpha dot. Okay, and this just labels, so alpha runs from 1 to 2, alpha dot runs from 1 dot to 2 dot, and this is literally just a 2 by 2 matrix. Do not be scared. Okay, so it's literally just these entries. 1 1 dot is that entry, 1 2 dot is that entry, and so on. Okay? So our matrix is p alpha alpha dot, and what does it mean that it has rank 1? It means that I can write p alpha alpha dot equals the outer product of two vectors, one of them which I'll call lambda alpha, and the other one I'll call lambda tilde alpha dot. Okay? So very concretely, let's say I had a particle moving in the z direction, then the p matrix would be 2e 0 0 0. And so what are lambda and lambda dot? Just most dumbly, lambda would be root 2e 0. Literally that vector, and lambda tilde would be root 2e 0. Say. Okay? And now lambda and lambda tilde, when you do a Lorentz transformation on the p, are acted on by L and R. Okay, so lambda and lambda tilde are acted on by one SL2 and the other SL2, because this is just a complex statement. So this is acted on by one SL2, either R or C, and the other SL2. Okay? Now, once again, this is really the only time in the course we're going to be careful about signatures and so on. We're going to be much more relaxed as we proceed, but it's very important to remember these things early on. In Minkowski space, in 3-1 signature, lambda tilde alpha dot is really the complex conjugate of lambda alpha. Okay, so lambda tilde 1 dot is lambda 1 star. And that's important in order for the matrix to be Hermitian. Okay? Yeah. If I want to hear from you, I will say something. Up to a sign. You're such a jackass. Yes, up to a sign. But just that's what you get for, like, you know, being someone's advisor. All right. All right. In 2-2, lambda alpha and lambda tilde alpha dot are just independent and real. Okay? And in general complex, lambda, lambda tilde are just independent and complex. Okay? All right. Now let's talk about what Lorentz invariants look like. So the Lorentz invariants that I can build are just either contracting lambdas, pairs of lambdas or lambda dots with the epsilon tensor. So for example, I can take lambda 1 alpha, lambda 2 beta, epsilon alpha beta. Okay? That's a Lorentz invariant. This one I can also call this bracket lambda 1, lambda 2. That bracket means contract with the epsilon symbol. Or it means stack these two vectors together to make a 2 by 2 matrix and take the determinant. Okay, all equivalent. Or if there's no confusion, we'll often write this as 1 2. Okay, so if there are particle labels lying around, the fact that it's inside this kind of bracket is telling you that it's a lambda that you're contracting. Okay, or I can contract two lambda tildes similarly. Okay, I can call that lambda tilde 1, lambda tilde 2, or when there's no confusion, I'll use square brackets for those guys. Okay, so these are nice Lorentz invariant objects. Let's see some familiar things from this perspective. So for example, what is P1 dot P2? Without thinking much, P1 is a lambda lambda tilde, P2 is a lambda lambda tilde for 1 and 2. So the Lorentz invariant P1 dot P2, ignoring factors of 2, is just angle bracket 1 2 times square bracket 1 2. Here's a slightly more fun one that you can play with. If you've done like field theory calculations, often you get traces involving gamma 5. So this is sort of a parity odd trace involving 4 null momenta. Okay? And you can rewrite this in terms of the little Pauli matrices as the trace of those little matrices P1, P2, P3, P4 that I was talking about. Okay? And you should compute these things and relate them to formulas that look like 1, 2, 2, 3, 3, 4, 4, 1, where I alternate between angle and square. That's a little exercise for you to play with expressions like that. All right? OK, but now let's come to the real point about this, which is why are we happy with lambdas and lambda tilde? You see, normally we'd have to think about this 4 momentum as some constrained object, p mu such that p0 squared equals p vector squared. Now the constraints are gone. You give me any lambda and any lambda tilde, and I build a p mu out of them. That's great. They're not constrained things anymore. The problem is that we know there's only 3 degrees of freedom associated with a massless particle, right? You just give me the spatial momentum, and that determines the energy. But there still seems to be 4 degrees of freedom associated with lambda and lambda tilde. OK? 2 in lambda and 2 in lambda tilde. Or said another way, when I write this formula down, p alpha alpha dot equals lambda lambda tilde, in fact, this formula does not uniquely fix lambda and lambda tilde. I can take lambda and rescale by lambda goes to t lambda, and lambda tilde goes to t inverse lambda tilde, and p goes to p. For example, if I'm in 3-1 signature, in general complex, t can be anything. In 2-2 signature, t is real. In 3-1 signature, t would have to be what? A phase, right? In order for lambda tilde to be the complex conjugate of lambda. So I can rephase lambda and lambda tilde, or rescale oppositely lambda and lambda tilde, and leave p invariant. Boo-hoo! But this is actually not a problem. This is the whole point. Because what is that transformation? It's exactly the little group, right? So it's something that leaves the momentum invariant, but lets you pick up a phase. And I won't go through this in detail. You should do it yourself, because it's literally exactly paralleling the story that we just went through for the Vikner little group construction. But let me just prove to you that these lambdas are exactly the objects that we want. Or I'll just sketch the proof, because it's exactly the same as the little group story. See, precisely because we can't uniquely associate a lambda and a lambda tilde with p, you do the same thing. You say, let me pick a reference k. K alpha alpha dot. For this k, I write it as lambda alpha for k, lambda tilde alpha dot for k. This is just, again, a definition. OK? Then I will write a general p as an L K R. OK, so this is writing, this is for the matrix, if you like, a particular SL2 cross SL2 transformation. And I will use that to define lambda alpha for p is going to be L alpha beta lambda beta for k, and lambda tilde alpha dot, let me call this L tilde. And lambda tilde will be L tilde alpha dot beta dot lambda tilde beta dot for k. Okay, so we're doing exactly the same thing we did before. We use this to just define what I mean, canonically define what I mean by a way of attaching a lambda and lambda tilde to every p. And now I can ask what happens when I do a Lorentz transformation on that p index. And what happens is that lambda does not go simply into L times itself, but it picks up a phase under the action of the little group. So we're literally paralleling the exercise that we did in the story of the little group. And so we see that these lambdas are exactly the objects we want. The lambdas, no invariance, no redundancy, no polarization vectors. The lambdas are the objects that have the property that when you do a Lorentz transformation on them, they pick up a Lorentz transformation on their Lorentz index, but also a phase, which is the little group transformation. OK? So this is the conceptually important point about spinor helicity variables. Not just they're simply a trick for representing massless particle momenta in a nice way, but that they make manifest the little group transformation properties. So that if we want to talk about an amplitude, so let me just give you an example so you see how cool it is. So here's a formula. Here's the first amplitude we'll write down. But imagine there's 4 particles. And here's a formula. It happens to only be written in terms of lambda brackets. This is very special. In general, they'll be much more complicated. But anyway, this is a famous formula. It's called the Park-Taylor amplitude. We'll talk more about it. Okay? But anyway, this is some expression in terms of lambdas and lambda tildes. It happens not to depend on lambda tilde. OK? But the beautiful thing is, I don't even need to tell you what the helicities of the particles are. This formula tells you what the helicities of the particles are. Okay, because in order to figure out what the helicities are, you have to see what happens to the amplitude when you do a rephasing. Lambda goes to T lambda. Okay, so what happens if I take lambda 1 and send lambda 1 to T1 lambda 1? Well, there's 4 lambda 1s upstairs. There are 2 lambda 1s downstairs. So this whole thing goes to T1 squared times itself. So that tells you that particle 1 has a certain helicity. It's a factor of 2 times the helicity of the basic spin-a-half representation. So it has helicity 1. In fact, the way we set things up just by convention is to say that the amplitudes are objects that have the property, they're functions of lambda and lambda tilde, Lorentz invariant functions of lambda and lambda tilde, but they have to have the property that for particle A, so A goes from 1 to n, however many particles there are, but if you rescale the nth particle, T, by T and T inverse for lambda tilde, you have to pick up Ta to the power of -2 the helicity of the particle, m of lambda and lambda tilde. That minus sign is pure convention, okay, but that is our convention. So with this convention, we actually say this particle 1 has what? It has negative helicity, helicity -1. And this formula tells you, you don't even have to tell it, the homogeneity of the amplitude under rescaling each variable. This formula, this captures all of the kinematic facts about the correct symmetry transformation properties of amplitudes. And so we learn that this is an amplitude where particle 1 has helicity -1. What about particle 2? No 2's upstairs, 2 2's downstairs. So here we get T1 to the -2. Therefore, particle 2 has helicity +1. So this is 1 minus 2 plus 3 minus 4 plus. Some amplitude for massless particles of spin 1 and of helicities -1 plus 1 minus 1 plus 1 in this way. OK? So for instance, we also learn that, let's say someone gave you this formula. This is an illegal formula. This formula means nothing. Okay? Because the 2/4 to the 4th, this is a totally different homogeneity, different rescaling. Right? So every expression has to have fixed weight under the action of the little group. Okay? So in fact, what would this formula be? It would be a formula for a different amplitude where 1 is plus and 3 is plus and 2 is minus and 4 is minus. OK? All right. Now, I was planning on saying a little bit about massive amplitudes, but let me we'll leave that for a different for a different time because I want to proceed with our main topic of interest here. OK. So now we have the objects that we're going to be talking about. Massless amplitudes from massless particles in 4 dimensions are not functions of momenta and polarization vectors. They're only redundantly so. They are functions of spinor helicity variables of appropriate homogeneity. Okay, so these are so now you finally see an actual amplitude. That's what it really is. Okay, and there's no redundant representation of it anymore. Okay. All right, so now I want to spend a little bit more time with these lambdas and lambda tildes, because already at this very early stage of just thinking about kinematics, we see some indications of the things that are going to come in the more irresponsible part of this course, that in thinking about amplitudes, we should start talking about things like Grassmannians. Okay? So if you're a physicist like me, you've never heard of a Grassmannian. Who the hell cares about Grassmannians? One of infinitely many things mathematicians care about that physicists don't care about. Okay? Grassmannians are the space of the space of k-dimensional planes in n dimensions is a Grassmannian GKN. Why the hell do we care about k-planes in n dimensions? Okay? But in fact, we're going to see why we have to care about k-planes and n dimensions already at this extremely primitive level of just thinking about kinematics. And doing this is also going to give us a picture for momentum conservation. Okay, so we're going to see that there's a novel way of thinking about something as basic as momentum conservation in a way that we're not used to thinking about, but which is kind of forced on us when we decide to think about amplitudes in this very invariant way. So let's just say that I want to just give you the data of, I have n particles that are scattering 1 through n, and I just want to give you the data of the lambdas and the lambda tildes. Right, so here's the lambdas. Here's lambda 1, lambda 2, up to lambda n. Each one of them is a two-dimensional vector. So I'm just going to stack them all together, and it's going to be a 2 by n matrix. OK? So literally, you know, this is some matrix A1, B1 for the first particle, A2, B2 for the second particle, AN, BN for the last particle. OK? So let me, and then there's also the same thing for the lambda tildes. Okay, so some A tilde 1, B tilde 1, A tilde n, B tilde n. Now, the way I've presented this, you're supposed to think about this matrix in terms of its columns. It's n columns. But let's say someone wanted to think about it a different way. Instead of thinking about it as n two-dimensional column vectors, they decided to think about it as 2 n-dimensional row vectors. Right? Nothing wrong with that. So now, of course, and this is the main, I think, novelty of everything we're doing in this course mathematically to a physicist is that we're always thinking in very high dimensional spaces. We're not thinking in 4 dimensions or maybe 10 dimensions, 11. We're always thinking in spaces with n's and k's and things that are arbitrarily big. And the beginning of it is this kind of inversion. So the 2 here has to do with the fact that we live in 4 space dimensions, and the Lorentz group is SL2 cross SL2. But now we're going to think in an n-dimensional space, where n is the number of particles that can become arbitrarily big. All right? Anyway, we do it. So that means, let's say, the A's is some giant n-dimensional vector A. This is the vector A1, blah, 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 AN. And there's some other giant vector B, B1 through Bn. So let's call this A. And because I'm not ashamed as a physicist, I even put a vector on top of it. OK, and B. OK, so I'm not ashamed. So good. So that's the data. Okay, that's the data of all the lambdas, 2 n-dimensional vectors. But you say this is a really lame way of giving the data, because someone in a different frame will do a boost. And when they do a boost, they're not going to have the A's and the B's. They're going to be different. Right? So someone in a different Lorentz frame is not going to give you the same A and B. They'll give you some A prime and B prime. OK, so here's some A prime for someone else and some B prime for someone else. And of course, the problem, this is an n-dimensional space. It's not 2-dimensional. But anyway, someone else is going to give you an A prime and a B prime. So what can we say? Is there anything about this picture that's actually frame independent? What's the Lorentz invariant content of the information in this A and this B? Okay, and here what really matters is that the Lorentz transformation is SL2. It's really simple. It's just a random linear transformation. So when I do a random linear transformation, my new A1 prime is something A plus something B. My new B prime is something else A plus something else B. But it's the same something else for every component, right? And that means in my new frame, the new A prime is going to be some linear combination of the old A and the B. And the new B prime is going to be some linear combination. So what does that mean? That means that the 2-dimensional plane that's spanned by A and B is actually exactly the same. So that's the cool thing. The Lorentz invariant content in the lambda data is actually a 2-plane in n dimensions. So that's all of a sudden why we're thinking about Grassmannians. We don't care about Grassmannians, but the reason why we care about vector spaces, right, is because it happens that the Lorentz transformation is in SL. It involves linear transformations. And that fact about the space-time symmetry of 4 dimensions tells you there's a natural way these things act on vector spaces, on planes, linear transformations. Okay? We already see this with the Lorentz group, and we're going to see it on steroids with the conformal group when we talk about twistors and momentum twistors and things like that later. But even with the Lorentz group, we learned something cool, which is that the data about the lambdas is contained in a 2-plane in n dimensions. All right, so let me now draw a picture. So all the lambda data is actually some 2-plane in n dimensions. So here it is. I'll call this a lambda 2-plane, even a little lambda 2-plane. There is some other lambda tilde 2-plane. So these are two 2-planes in n dimensions. Okay, so this is an n-dimensional space. Now, all the time from now on in this course, if you want to visualize anything, think all the variables are real. Okay? These are in principle complex. You're going to imagine all these variables are real, and therefore everything you're visualizing is in 2, 2 signature. Okay? But anyway, that's life. That's what we're going to do. We really imagine these are two 2-planes in n dimensions. Yes?
Is there a reason that A and B need to be independent?
Sorry?
A and B need to be independent?
Well, I mean, I'm just saying, I just hand you the lambda. They're just arbitrary. That's the whole point. You give me any lambdas you like, any lambda tildes you like, and that gives me some set of null momenta.
I'm just saying they might
Right.
not span a plane, they might span a line.
Oh, I'm coming to that in a moment. In fact, I'm coming to that, but generically they'll span a plane. You're right. It might degenerate further. That's exactly the topic I'm about to come to. Okay, but now there's a reason I've drawn it this way. So I've drawn it in a way that looks like lambdas are orthogonal to lambda tilde. Why have I drawn it that way? Because that's a statement of momentum conservation. Momentum conservation statement is that this lambda 2-plane is actually orthogonal to the lambda tilde 2-plane. Quite cool. Why is that? Well, what is momentum conservation? Momentum conservation says that the sum of all the momenta, the sum over all the particle labels, so sum over A of lambda A alpha, lambda A alpha tilde, lambda tilde is equal to 0. But that means take any vector in the lambda plane is orthogonal to any vector in the lambda tilde plane. That's the dot product summing over A there. Okay? So we see that something as basic as giving me the data of n particles satisfying momentum conservation is associated with this interesting picture of two different 2-planes in n dimensions that are orthogonal to each other. Okay? So the orthogonality here is momentum conservation. Now we're going to be coming back to this picture a lot later. But for now, let's finish this lecture by looking at the ramifications of all of these things for the simplest possible amplitudes that you might imagine talking about. Okay, so the simplest amplitudes we can talk about are 3-particle amplitudes. Two particle amplitudes don't mean anything. It's just giving the label of the particle. So the first interesting amplitude we could talk about is 3-particle amplitudes. And here, if you've had any exposure to field theory, if you haven't, as I said, it doesn't matter. But if you have, you'll be a little confused. And it might have always bothered you that when you draw Lagrangians and so on, for example, in Yang-Mills theory, you certainly have the feeling that this diagram is more important than that one in the Lagrangian. Right? Somehow this has the g in it. This is g squared. This is a slave to this, and so on. Somehow this is the most important thing, and yet you never talk about a 3-particle amplitude in your field theory. Have you ever seen, does anyone talk about what is a 3-particle amplitude in Yang-Mills theory? If you've taken, do you see it in Peskin and Schroeder or any other book? You don't see it, right? And well, there's lots of reasons. For example, people say if you have a massless gluon, you can't happen. I can't have a massless gluon split into 2 other massless gluons conserving energy and momentum unless it's exactly collinear, right? So the particle's coming along, so it's super duper singular. And if you force yourself to compute the amplitude, you'll find that it's 0. It's a little bit funny, right? That seems like the most primitive thing there is, and yet immediately you're talking about the next thing when you talk about amplitudes. And not correctly, deeply thinking about the 3-particle amplitude is, in a sense, the entire reason the development of this subject took 40 years to take off. Okay, because you have to learn to think about the simplest possible thing in the simplest possible best way, and then things proceed. It's a general fact of life about physics. If you don't understand the simplest thing in the simplest possible way, you're in bad shape when you try to understand more complicated things. So the 3-particle amplitude is the thing that we need to understand. And let's try to get some feeling for why it's hard. why it seems either trivial or impossible or zero. So in order to do it, let me jump to 4-particle amplitudes for a second. Many of you are more familiar with. So we said if I have a 4-particle amplitude, there's all kinds of things for it to depend on. I can take the momenta of particle 1 dot particle 2, momenta of particle 1 dot particle 3. Okay, there are these things like S, T, and U that we talked about before, but anyway, there's all kinds of Lorentz invariants for them to depend on. These amplitudes can depend on things. What about at 3 particles? What's P1 dot P2? It's 0. Right? If all the particles are massless, P1 plus P2 plus P3 is 0. So P1 plus P2 squared is P3 squared, which is 0. All the invariants are 0. All the kinematical invariants are 0. So what can the amplitudes depend on? Nothing, apparently. Yeah, that's why it's confusing. Maybe if you had a scalar particle, you could say the 3-particle amplitude is a number, is a constant, g. Right? And indeed, if you had a phi cubed Lagrangian g phi cubed, that's what it looks like. The Fineman rule would be g. You know, you're happy. There's no polarization vector to dot into. You're not so confused. But you also learn that if the particle is spin, somehow everything has got to be pure helicity information. Because I can make the amplitudes by dotting into polarization vectors. So all the p dot p's are 0, but I can make things that are non-zero by dotting the p's not into each other, but into polarization vectors. Or I could dot the polarization vectors into each other. And now this is an exercise, a very nice exercise you can do without ever seeing a Lagrangian or anything like that. Just try. Take 3 spin 1 particles, 3 epsilons, 3 p's, just dot them into each other any way the hell you can. And then impose at the end that if you take one of the epsilons and you replace it by p mu, you get 0. Then you lock down a very specific structure. In fact, 2 very specific structures. And those 2 structures are exactly what you get from Yang-Mills theory and a theory with a trace f cubed interaction, okay, which gives you 2 different possible structures that you can have. So even in the conventional way of doing things, that tells you that all the information in the amplitude is pure helicity. Okay, it's all about helicity and nothing else. But now, exactly that fact is going to make it possible for us to actually write down, with no Lagrangian, nothing, completely from symmetries, what 3-particle amplitudes are in terms of these spinor helicity variables. Okay, and to get going, let's think about what momentum conservation means for 3 particles. Okay, so that's where all the subtlety is what momentum conservation looks like for 3 particles. And, well, let's look at this picture. What do we have? I have a lambda, which is a 2-plane in 3 dimensions now. If n equals 3, I have to have lambda. Let's say here it is. Here's lambda. It's a 2-plane in 3 dimensions. So this is literally a 3-dimensional space. And lambda tilde is a 2-plane in 3 dimensions. Oops. I can't have 2 2-planes in 3 dimensions that are orthogonal to each other. So let's say lambda is generic. It's a generic 2-plane. What does that tell me? That tells me exactly what you were wondering about. It tells me that lambda tilde actually degenerates to a line. So the lambda tilde 2-plane is actually a line. So this is lambda tilde, which is in the direction orthogonal to the 2-plane. OK? Now, I drew this geometrically so you see why it's true. It's very easy to verify it algebraically if you don't believe me. Write down the formula lambda 1 tilde plus lambda 2 tilde plus lambda 3 tilde equals 0. And this is good practice with contracting, with indices, and so on, to prove that the only way that equation is consistent is either if the lambdas are all parallel to each other or the lambda tildes are all parallel to each other. But it forces either the lambdas to be parallel or the lambda tildes to be parallel. OK? So that's the degeneracy, the degenerate nature of the 3-particle amplitude. So there are 2 ways that it can happen. And we can represent the 2 ways by 2 different colors. So we say either the lambdas are parallel, and then I'll do that with a black dot. And this is the fun of this subject, is on a blackboard you have to decide whether this is a black or a white dot. Okay, but I'm going to call this a black dot for this entire course. Right? So this is a black dot. And you have a white dot. And this is supposed to denote the kinematic configuration where the lambda tildes are parallel. Lambda tilde 1 is parallel to lambda tilde 2 is parallel to lambda tilde 3. But the lambdas are generic. And this is the other way around. Lambda 1 parallel lambda 2 parallel lambda 3, and the lambda tildes are generic. And this makes sense for the complex momenta in general. It makes perfect sense in 2, 2 signature, where lambda and lambda tilde are independent. But we see why Minkowski space fools us, because in Minkowski space, we force lambda tilde to be the complex conjugate of lambda. So the only way this can happen is to further degenerate. If the lambdas are parallel, the lambda tildes are forced to also be parallel. Okay, so that's why Minkowski, if you're obsessed with amplitudes just in Minkowski space, you're not going to see the most basic place where they're non-zero. Okay, and again, as I've said many times, there's many indications of this subject. We have to be more adventurous and think that the time and all the signature, all these things are going to come out. This is another super basic one. If you insist that the only thing that ever matters is Minkowski space, you can't even start. These things are all zero. Okay, but they make sense for complex momenta, and they make sense in 2, 2 signature. Now, this tells us, for example, let's say in this black configuration, it tells us that because the lambda tildes are parallel, that all the brackets made out of the lambda tildes vanish. Like 1, 2 equals 1, 3 equals 2, 3. All of these things are just 0, because I'm contracting two things parallel to each other with the epsilon symbol. Okay, so all of these things are 0. And that, of course, explains why all those Lorentz invariants are 0. Remember we talked about like P1 dot P2 is like square bracket, angle bracket times square bracket, 1, 2. I should have commented that it's nice that there's angle and square brackets, because this has vanishing little group weight, right? Which is good, because the P didn't have any little group weight. Okay, that's fine, but that tells you that all these Lorentz invariants vanish. So we knew that anyway, but okay, good. There are nothing that depends on the lambda tildes. Only things depend on lambdas. Okay, so, but that then tells me the most general ansatz I could make for this amplitude. Okay, it's not an ansatz. The most general function I could write down for this amplitude. So let's say in the black configuration, I can have some power of these brackets, 1, 2, let me call it to a power a1, 2, 2, 3 to a power a2, 3, 3, 1 to a power a3, 1. That's the most general thing that I could have, and it has some g, some strength. Nothing else, because the lambda tilde brackets are all 0. Okay? But I also know how to determine these exponents, because if I tell you the particles of helicity h1, h2, and h3, then I know that if I rescale 1, this whole thing has to pick up a factor of t1 to the negative 2h1. So that tells me that a12 plus a31 is equal to negative 2h1. a23 for particle 2 plus a12 is equal to negative 2h2. And a31 plus a23 is equal to negative 2h3. That's 3 equations and 3 unknowns, so I can solve. Okay, so I'm done. So I know the most general 3-particle amplitude. So what can it be? Let's write it down again. So in this configuration, it can be, I can have 1, 2 to the h3 minus h1 minus h2, 2, 3 to the, again, just by symmetry, sorry, h1 minus h2 minus h3, and 3, 1 to the h3, sorry, what am I doing? Oh no, that's fine. Yeah, 3, 1 to the h2 minus h3 minus h1. Okay. All right, so that's what it is. Or, sorry, and that's all I can get in this configuration. Okay. Now, what about the other configuration? If it's all white, if it's a white, then it's the same thing, but with square brackets and with everything inverted. So it can be 1, 2 to the h1 plus h2 minus h3, 2, 3 to the h2 plus h3 minus h1, 3, 1 to the h3 plus h1 minus h2. Okay? So that's what it is for that one with some g. And here, and I don't even know ahead of time that the g is the same as g tilde. I should have said earlier that parity interchanges lambda and lambda tilde. Okay, that's pretty obvious. There's nothing else. It could be. But anyway, we don't even know ahead of time. G doesn't have to equal G tilde. This is just pure kinematics. Okay. Yes.
Is parity just L with the negative?
Sorry.
Does parity have negative?
No. Parity is not acted on with that L. Parity flips lambda and lambda tilde. Okay. So you see, the 3 particle amplitudes are completely fixed. They're totally fixed by giving the helicity weights of the particles. So in fact, now we can ask another question. So let me just say this. Yes.
What are you assuming here? There's no hard dimension.
No, nothing. It has nothing to do. There's no assumption, no Lagrangian, nothing. A 4-dimensional theory, the 3 particle amplitudes are nailed. And this is quite cool, because if you think about Lagrangians, you would naively think, but there's infinitely many operators I can write down. You know, I can write down, let's say even for scalars, I can write down phi cubed. I can write down d phi squared phi, more and more derivatives, more and more things. R cubed for gravity, more boxes, more d's. On shell, they're all identical. That's the point. Okay? So that's why you don't get fooled. And if you play with Lagrangians, you then have to do work, field redefinitions, equations of motion, blah, 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 to see that. But here we don't care about that. We're just writing down the answer. You give me the helicities, I'm done. Okay? So let me just give 5 minutes, because I want to just finish this, and so let's just do some very, very simple examples. So let's say I have particles just of all helicities 0. So just scalars. Okay? So it's just helicity 0. Well, this is just a constant. Duh. Okay? So we knew that. Let's do another familiar example. What about if I have a scalar? So helicity 0 and 2 fermions. So they have helicity, let's say, -½ each. This is y, some coupling, times 1, 2, if they're both negative. Very nice. Okay? That's the Yukawa coupling. What if you have, but already here we see something interesting. You say, well, no, sorry, there's one other thing I could have written down here. This is what it would be in the configuration where the lambda tildes are parallel. But what if I have the configuration where the lambdas are parallel? Then I could have also written down y over square bracket 1, 2. These things both have the same helicity weight. Okay? This would be the amplitude when the lambda tildes are parallel. This would be the amplitude when the lambdas are parallel. But I could, in principle, have both of them. But this is the one place we sneak in something about Minkowski space. Because we want to ask that when we go to Minkowski signature, the amplitudes just don't blow up and become infinite. So you remember, when we go to Minkowski signature, if the lambdas are parallel, the lambda tildes also have to be parallel. So with this formula, I would get infinity. That does not make sense in Minkowski signature. Okay? So I don't allow that. So I learned something, that if I want the amplitudes to be finite in Minkowski signature, they have to have the property that this amplitude is only there for 2 minuses. Okay? And furthermore, it's only there in the configuration where the lambda tildes are parallel. And the configuration where the lambdas are parallel, 0. All right? Is that clear? So that's the only ambiguity that's left. If you give me the helicities, there are 2 possible formulas I could write down. Right? I gave the 2 of them with the angle and the square brackets. But when the sum of the helicity weights, the sum of all the helicity weights, is either positive or the sum is negative, only one of them is allowed and the other one will blow up. Okay? So in fact, the answer is that if you now just give me the helicities, if you give me the helicities h1, h2, and h3, when h1 plus h2 plus h3 is positive, I use the one with the square brackets, so h1 plus h2 minus h3, etc., with some coupling g. And when h1 plus h2 plus h3 is negative, I use the other one. Now you can ask, what happens when h1 plus h2 plus h3 is 0? Okay, so that's a little bit confusing. We had an example here where they're all scalars, but here they're not different. Okay? So let me give you a funny example. So let's say I have a scalar, and now I have a helicity minus a half here and plus a half. Still a fermion coupled to a scalar. But now I can write down, so if this is momentum 1, 2, and 3, here's a nice formula. 1, 3 over 2, 3. That has the correct weights. Or I could write down the other way around. 2, 3 over 1, 3 with the other kind of bracket. I have two choices. They both have the correct helicity weights. This is something you've never seen come from a Lagrangian. Okay? And at this level, there's nothing wrong with it. You can write it down. But later next time, when we talk about, see, this is pure kinematics. And we're seeing the three particle amplitudes are totally fixed by kinematics. For any spin of 100 million, it doesn't matter, right? But we'll see that if we then demand consistency of 4 particle scattering, the vast majority of these theories are inconsistent. Okay? And it's just a completely algebraic problem, beginning with these 3 particle amplitudes, to find what the possible consistent theories are. And those are the theories that we know and love. Gravity, Yang-Mills, supersymmetry, and all of these weirdo things where h1 plus h2 plus h3 is 0 are in fact excluded. Okay? But at this level, there's nothing wrong with them. But we later find out there is something wrong. So let me write down just a final thing before we let these guys in. Let's say, just to do another example, let's say we have particles of spin s, overall spin s. And now let me do the case where 2 of the helicities are minus and 1 of them is plus. Okay, so this is particle 1, 2, and 3. Then this amplitude is, just plugging into our general formula, is 1, 2 cubed over 1, 3, 2, 3 to the power of s. Really beautiful. So if I want to know the amplitude for Yang-Mills, yeah, that's what it is. In fact, how do I know it's Yang-Mills? There's one other amplitude that I could have. What if all of the helicities were minus? So those are the possibilities, right? Either 2 are minus, 1 is plus, the other way around, or all are minus and all are plus. So let me look at the other case where they're all minus. The one where they're all minus, the amplitude is 1, 2 times 2, 3 times 3, 1, all to the power of s. Okay? And now let me translate this to language that you know and love. This case is clearly more important at low energies than that one, right? Because it has some things downstairs. These pairs of brackets of units of momenta. Right? So whatever this overall coupling constant is has a lower mass dimension than that one. Okay? And in fact, this for s equals 0 is what you get from Yang-Mills. For s equals 1, and for s equals 2 is what you get from GR. Quite amazing. If you've ever stared at the GR Lagrangian expanded around flat space, it's not a walk in the park to write down the 3-point coupling. It has 90 terms in it in the Donder gauge. Okay? Not remotely a pleasant thing. If I ask you to figure out the 3 particle amplitude for gravity from that perspective, you would think I was very cruel, right? And yet, not only can we just write it down without doing anything, I'm just waving to Matt, but we discover another really interesting thing, which is not remotely obvious from the Lagrangian, that the 3 particle amplitude for gravity is the square of the 3 particle amplitude for Yang-Mills. Is that obvious when you write down the GR Lagrangian and the Yang-Mills Lagrangian that there is this relationship? No, right? That's one of infinitely many things that's obscured by the Lagrangian. On the other hand, what is that guy? These are what you'd get from an f cubed operator. It's a higher dimension operator. What you get from an f cubed operator for spin 1, and for spin 2 is something you get from an r cubed operator. And then in Riemann cubed operator if you're doing GR. And then I answer Andy's question again. You might think, but there's zillions of operators you could write down. Yes, there are. They all give you exactly 2 amplitudes, either the top one or the bottom one. And you don't even have to think about it or think about how you do field redefinitions, equations of motion, et cetera, to deal with it. The final thing I'll say about this is not only that it was simple to write down, but it has a disturbing feature. The disturbing feature that we didn't see here, See here, the amplitude is g, and here it's just something with brackets upstairs. The very disturbing feature is that these amplitudes have brackets downstairs. See, normally when you have things downstairs, you think they can blow up somewhere. And when amplitudes blow up in field theory, that means that maybe you produced a particle, there's a resonance, something, but there's no excuses for that here. Just a 3-particle amplitude. It's very peculiar and weird to have these poles in the 3-particle amplitude. And notice very interestingly, they happen exactly in those theories which in conventional language we need gauge symmetry to describe. Okay? Yeah. So we're going to be coming back to that next time, but I want you to keep that in mind, that the presence of those poles in the 3-particle amplitude is going to be the beginning of some drama that we'll see next time. All right, thanks a lot. Yes. So let me apologize to Matt. Sorry, Matt. Sorry about that. Sorry. I promise not to keep doing it.
We'll see.
Yeah, we'll see.
I was very impressed.
Yeah. Huh?
I was very impressed.
So was I. Yeah. Do you want this?
I know.
Yeah.
Makes that much less sense. Right, in order to have you have a normal the point that you take the quotient of the space of the space of gauge.
Because I was with the particle physics group, not with the
Yeah.